Hello everyone, this is Gunther here. Today I'm going to walk you through the architecture of configuration of high-speed software-defined radio mesh network built on three open source building blocks: OpenWiFi and BATMAN-adv and Zynq FPGA hardware. And by the end of this presentation, you will understand how these pieces fit together to run a piece of SDR hardware into a field deployable self-healing mesh router. And I put a source and a website with all information, and I put a hardware and diagram and everything, so you can understand everything. Now let's go into system architecture overview. Now let's start with the big picture. The system actually is a complete open source RF stack. It combines hardware accelerated baseband processing from OpenWiFi with kernel-level mesh routing from BATMAN-adv and turning SDR hardware into a field deployment MANET router. And because the baseband MAC and PHY operation run a field deployment MANET router, and because it's run directly inside the FPGA fabric and achieving about 10 microsecond of SIFS, actually timing, the Zynq dual core ARM CPU is left free to run Linux applications, video encoding and mesh routing daemons. And critically, this bridges is video encoding and mesh routing daemon, and critically this bridge transparent any local device, a PC on gigabit Ethernet, a phone on USB or LAN, automatically connect to multi-hop router with zero custom software. Now let's go into here component mapping across the OSI stack. Here you can see how each pieces of the system map into the OSI model. At the top layer 3 and above, the Linux kernel handle IP traffic, video and voice, reticulum, ATAC, and layer 2 routing is handled by BATMAN-adv, running as the BAT0 interface, providing dynamic multi-hop routing. And below that, OpenWiFi Linux driver operates at the lower MAC layer, exposing a standard MAC 80211 interface. And at layer 1, the Zynq 7020 FPGA fabric does the heavy lifting, OFDM PHY processing, CSMA, CA, and 2x2 MIMOs. And at the very bottom, the AD9363 transceiver or AD9361 unlock the 40 MHz handle RF direct conversation and IQ. The key takeaway: the FPGA absorb all the timing critical work, so ARM cores stay free for everything else. Now let's go into here to OpenWiFi versus BATMAN-adv. It's worth pausing to clarify the difference between these two technologies, because they operate at a completely different layer. OpenWiFi is a layer 1 and lower layer 2 technology, an open source FPGA based 802.11 Wi-Fi implementation. It's handle RF symbol framing, preamble detection, and CSMA CA channel access. And Linux just see it as a normal wireless interface. And BATMAN-adv, on the other hand, is a layer 2 data link technology, Linux kernel modular that completely radio agnostic. It does not care what carrier actually it's a traffic. It's just like an Ethernet frame, and routes them dynamically across multi-hop network using a global MAC address lookup table. Now let's go into detailed comparison points. Let's go level deeper in three specific dimensions. First, look hardware dependency. OpenWiFi required the specific Zynq FPGA and AD9361 or AD9363 combination, while BATMAN-adv will run on any standard Linux device with any network port. And second thing, packet handling. OpenWiFi deals with RF symbol framing and channel access, while BATMAN-adv builds a dynamic MAC address lookup table across hops. And third, frequency control. OpenWiFi directly dictates center frequency and channel width, while BATMAN-adv is entirely unaware that the frequencies even exist. It just sees Ethernet frame. Now let's go into when and why to combine them on Zynq platform. So why run both together? Three scenarios make the case. Number one scenario, heterogeneous hardware network. When you got OpenWiFi SDR nodes, standard Wi-Fi access point, and wired Ethernet link, all in the same deployment, the BATMAN-adv bridge them into one unified layer 2 switch. And another thing, the fast moving tactical MANET like drones and mobile units cause rapid signal fluctuation, and BATMAN-adv transmit quality algorithm updates routes instantly to prevent like dropping connections. And another thing, the multi-radio channel diversity. You can run a fast 5 GHz OpenWiFi link alongside a long range sub gigahertz LoRa backup, for example, and BATMAN-adv will automatically fail over between them. Now let's go into here to unlocking the AD9363 transceiver. Now let's talk hardware. The AD9363 chip found on boards like the Pluto Sky Revision 2 is physically identical to the higher end AD9361, for example. It's just factory restricted in software. So once you unlocked it into AD9361 mode, the RF tuning range expand from narrow, I think 3 to 5 megahertz to 3.8 gigahertz window without to full 70 megahertz to 6 gigahertz range. Maximum channel bandwidth double from 20 to 40 megahertz, for example. and you gain access to all major band you actually want in the field, like 433, 868, 915 megahertz, or 2.4, or 5.8 gigahertz, plus fine grained control over gain tables and baseband filters. Now let's going to here to unlocking commands in Linux, like U-boot. Here exactly how you do that unlock. You set two U-boot environment variables, as you can see, like attr name and attr value, both set to AD9361. Usually you can using the firmware setting this persist across reboot. So after you reboot the system, the driver initialize with the new profile. You can verify it worked by reading the IIO device name from system FS, and you're looking for output AD9361 PHY, which confirm the chip is running and in unlocked mode. And now let's going to here to this slide 9, maximizing through output using 40 megahertz and 2x2 MIMO. With the chip unlocked, you can maximize through output, like for example the Proto-Sky Revision 2 board per the Zynq 7020 FPGA, running the OpenWiFi logic and 2x2 MIMO cores. With the now unlocked the AD9363 running at 40 megahertz channel across two independent TX and RX chains, and it giving us two spatial streams actually. All of that connect to the outside world over the gigabit Ethernet. In practice, this configuration status 80 to 100, I think, megabyte per second of real TCP and UDP through output, with a PHY rate up to maybe 200 megabit per second at MCS 15. Now let's going to through output metric here. This chart put those numbers side by side. Single stream 20 megahertz like tops out around 65 megabit per second at the PHY layer, and roughly 30 megabit of actual net TCP through output after overhead, and move the 2x2 MIMOs over 40 megahertz channel, and the PHY rate jump all the way to like 200 or 300 megabit per second, and with real world net through output land in that 80 to 100 megabit range, as long as you maintain at least 25 dB of signal to noise ratio. Now let's go into OpenWiFi high speed driver initialization. Now let's walk through the actual configuration pipeline, starting with step 1, initializing the OpenWiFi driver for high speed. We bring the SDR0 interface down, then configure it from 802.11n with a 40 megahertz HT40 channel and dual stream MCS rate 80 through 15. We set it to ad hoc mode, bring the interface back up, and finally join the high-speed mesh network on channel 5180 using HT40. Now let's go into BATMAN-adv kernel modula and bring bridge integration. Step 2 is bringing up BATMAN-adv and bridging it with our local interface. We load the BATMAN-adv kernel module, add the SDR0 radio to the BATMAN-adv routing engine, and bring both SDR0 and BAT0 up. And then we create a Linux bridge BR0 and attach our Ethernet port, our USB-C LAN port, and then BAT0 mesh interface to it, and unifying everything into one layer 2 network. Finally, we assign the node and IP address on that bridge. Now, verification and performance diagnostic. Step 3 is verification. First, we run batctl in to confirm BATMAN-adv has actually discovered its neighbors over the RF link. Then on the receiving node, we start IPR-v3 in service mode, and on the transmitting node we run an IPR-v3 client sending at like 8 megabit UDP stream under clear line of sight. Condition you should expect to see like 80 or 95 megabit per second of UDP through output with low jitter, and confirming the link is performing as designed. So finally, to bring it all together, FPGA accelerated the OpenWiFi handle the baseband PHY and MAC timing, freeing up the ARM cores for routing and applications. BATMAN-adv layer on the top of deliver radio agnostic self-healing multi-hops, routing across RF, Ethernet and USB-C interface simultaneously. And by unlocking the AD9363 into AD9361 mode, we unlock 40 megahertz 2x2 MIMO operation, and pushing sustained through output up to 80 or 100 megabit per second together. That's a complete open source RF stack from the FPGA fabric all the way up to the field deployment mesh network. Okay everyone, thank you for watching, and actually I am waiting to order 2 hardwares and build a firmware for this specific topic, mesh routing MANET, and I will add everything information in the future. Now you can go to reference website I make, and the example of SDR hardware and schematic and everything you need to clear everything to you. Okay everyone, thank you for watching. This is Kanfar here, and bye bye.